So thus far, we've talked mostly about building structures. We've mentioned other infrastructure works occasionally, but we've focused on building. This is partly because this is a course that's coming from an architecture program, so buildings are naturally what we would focus on. But building extends beyond the sort of traditional architectural form of building, and there are other key forms that we want to look at as well that offer us insight into how materials and techniques and design strategies evolved as well. And one of the key building types that's not an architectural building is, of course, bridges. This is where structural engineering probably ends up being the most dominant force in what the final form of the building is. And in the words of David Billington, bridges are sort of naturally one of the places where the structural art, as opposed to the structural discipline or the structural science, really happens. So I want to look at the bridges that were in particular built during the 19th and early 20th century and show how these new materials that have come online, iron and then steel and of course concrete, have influenced the forms and also the design of bridges as well as more traditional buildings. We talked a little bit about one of the key innovations in bridge design when we looked at iron and the role that iron played in industrialized building. And the sort of the leading iron project of the mid 18th century was, of course, Coalbrookdale Bridge, this prefabricated cast iron structure that was built in the coal and iron district of Great Britain. And we talked a little bit about how it reverted to the semicircular arch, which by this point it's known that that's not the perfect shape, but it is a shape that lends itself to repetitive fabrication because you can make the arches of the bridge from a single mold that's set to a single radius, or in this case, 3 radii that each would have a different mold. And we've talked as well about the difficulty of connections in cast iron. You see a couple of these at the base. Rough, not very precise, but in this case held together with shims, or things that are pounded into the joints to keep the iron in place. Coalbrookdale was really proof of concept of iron as a structural material, but it was also proof of concept of iron as a bridge material, as something you could use other than timber or stone, which were the only real materials that had been used to that point in bridge design since the Roman era. Very quickly, iron catches on as the sort of natural material for bridges, particularly bridges that are built out in the countryside, where you have to take material and sort of send it out to a fairly remote area. Because it's efficient in that, a pound of iron can carry much more than, say, a pound of stone or a pound of brick. This meant that transportation was relatively easy. And the first sort of wave of bridge building in the early 19th century came about really for road bridges that horses and carriages would go over. And among these, Thomas Telford is one of the figures we think of as kind of the father figure of the iron bridge, taking what was learned at Coalbrookdale and turning it into a more replicable type of building structure. Telford came from an agricultural background. He worked as a stonemason in Edinburgh, so went to the big city and learned a trade, and met the architect Robert Adam in London, who was influential in getting him to think about these new technologies that were coming online and how those might change the discipline of building that he was involved in. He rose to become a sort of public figure. He was the surveyor for public works in Shropshire, and this meant a great deal of work on preserving and restoring, in addition to building new bridges, along with other infrastructural projects, aqueducts and canals in particular. A massive flood that occurred on the Severn River and the survival of the Coalbrookdale Bridge alone. In other words, the other bridges, stone bridges and masonry bridges, were washed away by the force of the flood, but Coalbrookdale remained, convinced him that iron was the ideal material because it was not only lightweight and very strong, but you could also make bridges that were porous, that would allow floodwaters to simply flow through them. 14 years after he became the sort of county surveyor, he became a civil engineer for the whole country of Scotland and was responsible for over 1,000 bridges throughout the countryside, including a couple that we'll take a look at here. And this is really important, right? The idea that iteration or coming back to a similar project again and again and again allows engineers, allows builders, allows architects to really refine their approach and to come up with ways that are increasingly more either structurally appropriate or more efficient for the sort of spans that they're being asked to cover. You can see writing here about Bonar Bridge, Telford really sort of got the definition of structural art that this engineer and historian David Billington, who has some readings in the weekly reading list this week, came up with, right? To improve the principles of constructing iron bridges, right? So constructing them, right? The mechanical cause of the structure, also their external appearance, so what they look like, thinking about making them as beautiful as possible, and to save a very considerable portion of iron and consequently weight. So that is the performance aspect. So there it is, right? Telford hits on the three themes of the course, that he has to integrate both the performance of the bridge, but he also has to think about how it is fabricated and assembled efficiently. And he's worried, of course, about whether it's beautiful or not. And Telford's sort of standard approach was to think about the cast iron bridge as an arch and a deck and a web. The arch in this case is all cast iron elements that are doing most of the work, carrying most of the load in compression. The deck is designed so that it has the gentlest slope possible for the carriages that are going over it. And then his real genius was to understand that by connecting the two, you could make the bridge behave in a more efficient way, that the bridge, as we were talking about concrete, this is a way of making cast iron, if not monolithic, at least hyperstatic, that connecting the deck and the arch means that loads have millions of different paths they can follow as they reach the abutments. The deck and the arch are working together, essentially. You can see that it's made up of cast iron elements that are bolted together, again, relatively loosely with shims. So these bridges required constant maintenance. But cast iron being very good in compression, they did it with very little material. And you can see that particularly in the Bonar Bridge on the left, where the approach arches are built of masonry and obviously are incredibly heavy, require huge foundations to support the dead weight of those approaches on the river soil below. Whereas the iron bridge, the part that Telford is doing in the middle, is incredibly lightweight and incredibly porous, so that floodwaters, again, can flow right through the sort of truss or the web between the arch and the deck. The Scottish poet Robert Southey, when he first saw Bonar Bridge, wrote about it, a quote that I think is worth repeating. He said, "As I went along the road by the side of the water, I could see no bridge. At last I came in sight of something like a spider's web in the air. If this be it, thought I, it will never do." In other words, it will collapse. But presently I came upon it, and here's a poet talking, remember, and oh, it is the finest thing that ever was made by God or man. So a poet seeing this, what must have to his eyes seemed like this most lightweight, incredible span ever, right? A new sense of scale, a new sense of proportion, a new sense of what we might think of as structural finesse almost. And here in detail, you can see that the arch is very clearly cast iron. The web is wrought iron. Those are rolled angles that are connecting the deck and the arch. And remember, wrought iron is reliable in tension in ways that cast iron is not. So the web is doing the work of connecting the two. It's able to take both compression and tension and make the deck and the arch behave together. And to do this with a remarkably small amount of material. Telford understood the potential for iron in bridges and among other things designed this, what would have been about a 400-foot span in cast and wrought iron for London Bridge. And there is a multi-arched span there today. Telford thought, theoretically anyway, that it could be done in a single span. So very much like the concrete bridge over the Tiber that Onnabeek would do a century later, here is a proposal to span the Thames in one go in a way that would have been both spectacular and of course, record-breaking. Telford also worked with this sort of opposite idea that in addition to using a compression arch to carry a deck over a long span, you could use what is essentially a tension arch. That if you used wrought iron instead of cast iron, and you built towers to elevate the wrought iron tension arch, you could make what we now know as the suspension bridge. And really the first large-scale versions of these was over the Menai Straits in Wales. Telford's scheme here was to build these two giant compressive structures that would lift the wrought iron chains up above the deck far enough that you would get a little bit of a catenary shape, right? Not a full catenary, but enough that the chains are always going to be in tension. The weight of the deck puts a consistent load on the chains, so they take that shape naturally. They go over saddles on top of the towers, and they're connected to backspans. And you can see that there are cables that then go into anchorages in the land, and the anchorages basically hold the cables and allow them to develop a huge amount of tensile force within them. You can see that the approach decks have cables running down to them that are basically holding the main cable down, making it maintain its shape. And this allows you then to have a balanced load on the other side, which is the weight of the deck rolling between the two compression towers. If you look on the right, you can see a more recent photograph of the Menai Straits Bridge being painted or maintained in some way. And you can see that the chains are actually made not of literal cables, but of wrought iron bars. So there are hundreds and hundreds of these that are bolted together that basically function like a chain. Even though they're large solid bars, there are enough of them bolted together that they take up the catenary shape when under loading. So Telford was obviously a brilliant bridge designer, came up with new forms and compression and tension that exploited the characteristics of these two new materials, cast and wrought iron. But he was also a bit of a theorist, a bit of a philosopher about engineering. And his approach is sort of uniquely British. If you know anything about the history of philosophy, you know that there are these two opposite schools. There's the British school, which is an empirical one, which thinks that we only get our knowledge through engaging with the world, right? Actually sort of bumping up against things and experiencing what makes them work. The so-called continental school of philosophy is more theoretical, based on the thinking especially of René Descartes, who thought that you could solve problems by simply sitting back and thinking about them. A theoretical approach versus the British approach, which we call empirical, right, from the ground up instead of from the top down. And Telford was described in the most empirical way possible by one of his proteges in this encyclopedia of sort of great people of the city of Edinburgh. And he puts Telford in a lineage with Newton, so very much coming out of the Enlightenment. And this is one of the themes of the last couple of weeks, is that the Industrial Revolution is really a product of the scientific advances that happened 100 years or so before. And he says that it was Newton that opened the path of mechanical science. In other words, not just thinking about science as mathematics, but actually conducting experiments, right? Looking to see what happens in the real world, the very definition of an empirical approach. And he says, this is Telford being quoted, "If the deductions of theory were to be followed, they may lead to the proposing of weakness instead of strength and craziness instead of stability," right? If all we do is trust our own minds to think through a problem, we're going to come up with bad ideas, right? He says, by contrast, give the modern engineer only a sure foundation who will raise the structure as durable as the materials of which it is composed. In other words, the engineer knows how to actually engage the world, right? To get his hands dirty, to go out there and figure out what to do with the materials that the world gives him. And Telford, quoted again, says that theories led to no one useful practical result. That's a bit of an overstatement, I think, but nevertheless, as to the thickness of archstones, sidewalls, and piers, the math, the science isn't catching up with the experience that engineers have had actually going out and building these things. If we leave it to theory, we're still left in the dark, and we ought to go out instead and actually build. This is the great British tradition, right? That we figure things out by going and getting our hands dirty. And some of this in the 19th century comes along because there is a major building campaign that connects the entire island of Great Britain through the railroad. And the railroad is this invention that utterly transforms Britain as a country. Eventually it'll transform the United States as a country, Europe as a continent, eventually even Asia, Africa, right? It spreads throughout the world. But it is invented in Britain, and it is for many, many years essentially a British invention. And we think of the railroad as the invention of the steam engine and making the steam engine portable by putting it on wheels. But in fact, it is also the invention of a new network, right? Rails have to be built for these machines to travel on. The pioneers of the railroad are George and Robert Stephenson, a father and son team. They are from a mining family, and the father was the so-called engine wright for a mine in the central part of Great Britain. In other words, he was responsible for developing and maintaining the machines that would lift coal out of the ground, or drag buckets of coal out of the ground, or run the pumps that kept water out of the mines. And by 1814, he had the bright idea that instead of having a stable steam engine that would pull carts on ropes, you could mount the steam engine onto the carts themselves. And if you gave them a proper set of rails, which he thought you could do in cast iron, you could make a much more mobile, much more agile transportation system. And this had an incredible impact, first on mining, but then on the distribution of coal throughout the country. The two of them, George and Robert Stephenson, built the first railway in 1821 that took the product of the mines to a nearby town. And within a few years, they were reliable enough, safe enough, that they were able to carry passengers, right? Not very many, not very fast, but by 1825, there's both a freight and passenger use for the railway. They build the Liverpool and Manchester in 1830. This is the first commercial passenger and freight railroad. And in extending the network out over Great Britain, they run into a problem that's going to define bridge design in Great Britain for the century. And that is that while the steam locomotives are very powerful, they are only efficient at very, very shallow grades or slopes. And this is even true today. Rails have to be laid to very, very, very shallow gradients. In the early 19th century, even shallower than today, so 1/250, which if you think about the gentle slope of a 1 in 20 ramp, this is an amazingly flat hill that you have to get up. Bridges at the same time had to be designed to experience much greater dead and live loads than they had ever had before, right? The steam locomotives are heavy. They are basically point loads on a bridge instead of distributed loads. And so the road bridges, the methods of designing road bridges throughout Great Britain were obsolete when it came to railways, right? There's still a road network. Those bridges are going to stay. But all of the railroads not only need new rails, but they need new bridges as well. The bridge decks have to be very flat, so you can't have these giant steep arches that you can have with road bridges, and they need to be designed again for massive loads. The Stephensons build bridges for their networks. Some of them work, some of them don't. There are collapses, most notably at Chester in 1847, which begins to make people question the reliability of cast iron in bridge design. And as we'll see here in a second, the Britannia Tubular Bridge, which proves an awful lot about wrought iron in 1850. We've looked at that before. We'll take a more detailed look here in a second. There are other engineers who also work on the problem of rail bridges. The greatest of these is Isambard Kingdom Brunel, who's kind of the patron saint of English engineering. He was a child prodigy, a math whiz, and he worked for his father, who was a civil engineer, on the project to dig a tunnel under the Thames River. And this injured him badly when it flooded, but the sort of failures that accompanied that seem to have driven him to try to do greater and greater things afterwards. A rival railway to the Stephensons, the Great Western, made him chief engineer in 1833. He designed sheds, some of which we've looked at. Paddington Station was one of his, but also bridges, and the first transatlantic steamship to sort of extend the rail network to the so-called New World or North America in 1838. The Britannia Tubular Bridge was one of the Stephensons' works. They again hired William Fairbairn as a consultant. Fairbairn, the great engineer who developed, in many ways, the I-beam that we looked at a couple lectures ago. The Britannia Tubular Bridge goes over these straits between Wales and Great Britain, and it had these very, very stringent requirements from the Royal Navy, who wanted their ships to be able to pass underneath it unobstructed. So the key, you might remember from the lecture on Fairbairn, was to make the bridge decks basically like giant I-beams. So a concentration of wrought iron on the top and bottom that are like the flanges of an I-beam, the pieces that do the real work, and then thinner webs on either side that connect the two, that make them work as a beam instead of as isolated elements. The genius of this was not only in the performance, but also in the lifting of the tubes. So you can see on the right some drawings of the lifting equipment that was put into the towers. And here you can see an illustration of the tubes being fabricated on the shore and then relatively quickly being floated out into position and lifted into place. And this was so that the river didn't have to be shut down to marine traffic for any length of time. The tubular bridge was a huge success. It was the model for a couple of other tubular bridges, but had some problems as well, not least of which was the accumulation of smoke within the tubes. But there were problems that developed with the webs as well. The webs were a little too thin and tended to buckle in ways that the Stephensons hadn't anticipated. The bridge was fine. It never collapsed. It is intact, somewhat restored and rebuilt today, but it's still there. It didn't prove to be a very valid model, though, for long span railroad bridges. We don't see a lot of tubular bridges around today. A sort of an alternate version or a different way of thinking about the same problem was put forward by Brunel, who looked, instead of looking at the bending properties of a typical beam shape like Fairbairn would have naturally, Brunel looked at both tensile and compression arches as ways to span huge distances. And so here, Saltash on the other side of Great Britain, where he has a similar problem as the Britannia Tubular Bridge, Brunel comes up with this ingenious double arch system that carries the deck over these massive 450-foot spans. Like the Britannia Bridge, these rely on great big towers and huge, long approaches and probably tunnels on either end to get the very, very shallow grade for the trains. But then you can see that Brunel does something very ingenious. He builds a tension arch, a cable arch, that is draped from the two towers, just like a suspension bridge. But to avoid the problem of the backspan and to avoid the inward thrust that those cables will put onto the towers, he builds a second arch in compression that goes the other way, right? The tension arch is the positive curvature or the smiley face. The compression arch is the negative curvature or the frowny face. The thrusts on those two cancel each other out. The compression arch wants to push the towers apart. The tension arch wants to pull the towers together. It therefore requires no buttressing and it requires no backspan like a suspension bridge would. It's an odd-looking bridge, but nevertheless, the principle is absolutely sound. And as you can see, the bridge did its job, right? It certainly spanned successfully. Brunel also designed suspension bridges. This is one in Bristol, the Clifton suspension bridge that is still there, that has the same principle as the Menai Straits, wrought iron chains made up of these very, very long eye bars bolted together, supporting the deck, and then you can see the cables run through the tower. They have to sit on a saddle that lets them move a little bit so the bridge can bend instead of break, basically. And then cables that run into giant anchorages that are sort of wedged into the landscape. These two methods, right, arch bridges and suspension bridges, go some way to solving the fabrication problem. You can build a bridge out of a lot of small pieces, ship those to the site, and put them together. But they rely on, in the Saltash case, very, very careful calculation, right? Tuning the arches very precisely so that the thrusts cancel one another out. In the case of the suspension bridge, an awful lot of work goes into getting the towers up high enough, the compression structures up high enough, so that you can make the tension system work. All of that works fine in a country like Britain, where you already have sort of reasonably good infrastructure. You can move things around, and you have factories and brick-making facilities that are never going to be too far away from your bridge construction site. When the railroad comes to America, however, there is a much vaster piece of land that the railways are going across. And it becomes really, really critical that more and more of the bridge can be prefabricated, right? Can be made in the iron foundry, put onto trains, taken to the end of the line, and assembled on site. There are not good quarries near all the places that the railroads want to build bridges. There are not good brick-making facilities near the places that railroads want to make bridges. And putting stone or putting brick onto rail cars is inefficient, right? The heavy material requires an awful lot of fuel to get it out to where it needs to go. So in the United States, the sort of standard issue rail bridge becomes the truss. And the truss bridge is a way of breaking the span down into hundreds of smaller pieces, all of which can be put onto rail cars fairly efficiently, taken out to the end of the line where the bridge construction site is, offloaded and pieced together by relatively unskilled labor, right? It takes iron workers, but the iron workers basically just have to know which parts to bolt together, and they can build the bridge even hundreds of miles remote from the nearest engineering firm or manufacturing facility. On the right, you see some of the types of trusses that were patented in America during the 19th century. All of them basically rely on triangulating the span. In other words, taking the what would be a very, very deep steel beam, say, and turning it into a series or a network of triangulated panels. And you can see that what that does is it fixes all the points of the truss into space. It means that the truss can't deflect because triangles don't change their shape. And that means that the load on the deck has to go into all the members of the truss. And you can do some very simple calculations to figure out how loads will flow through that network of triangulated cords. Of note, you can see that most trusses, you can tell the difference between members that are in tension, which can be very, very skinny, and members that are in compression, which for the same load have to be thicker because they are subject not only to crushing, but also to buckling. So for instance, in the Fink deck, the truss that is right here, you can see that the tension elements are on the bottom. They're always supporting the compression struts that hold up the deck. It's very, very clear where tension is happening and where compression is happening. If you think about it, that is analogous to the way that a beam works. All of these truss designs are basically designed to mimic the behavior of a beam, to put a compression element on top, a tension element on the bottom, and to fix the two pieces in shear so that they work together as a beam. Trusses can also get used, though, to make arches more efficient. And one of the great kind of hybrid projects is the Eads Bridge, which is named for its designer, James Eads, built in 1874, the first bridge to cross the Mississippi at St. Louis, and a really, really key piece in connecting the eastern United States with the West by rail. And you can see what Eads has done here. He's taken Telford's idea of connecting the arch and the deck, and now here he's using both wrought and cast iron, probably more wrought than cast iron, to build the arch at the bottom. That's actually a beam arch. It's a very shallow arch and therefore subject to a little bit of bending. The deck is fixed to it with these struts that mean that the two work together. And on the right, you can see that it's not only a structural idea, but it's also a constructive idea, that Eads finds a way to build the bridge without scaffolding, without having to impact the flow of river traffic below. The arches are built out from the foundations. They have these tension elements that are built on temporary tower structures that basically work to hold the arch, the end of the arch up. The two arches kind of grow outward piece by piece, and you hope meet precisely in the middle. Once they're connected, they can stand on their own, and you can use those arches then to build the deck above. In the next segment, we'll talk about one bridge in particular that really makes iron construction sets a new standard for iron construction in America. It connects not two pieces of the country, but two parts of a city. And it becomes iconic not only for what it does as a piece of engineering, but also what it does as a civic building, how it represents the connection between these two cities.